Hello, y'all. Continuing as we were discussing on yesterday, 2 days ago, about the transformation, preparing for my classical dynamics class. So remember last time, off camera, I had figured this out. I don't remember exactly what I did. So today we're going to look at it and see about figuring out exactly what the process is. So the idea, this is from the classical dynamics textbook. The idea is that we have this point P, which I'll highlight here, and we have the normal, as you can see, coordinate system XY, and we have the alternate coordinate system XY, X prime, Y prime, and we're basically putting the um, point P in terms of the other coordinate. So I took in, put actual numbers onto this thing to make it easier. I know sometimes at least for me at least, the sort of, what, I forget the official word for it, um, symbolic. The symbolic form can be a bit confusing. So put actual numbers in there and worked it out. So we'll see if we can backtrack and try to get it in the normal uh, form that the book is talking about. So this is section 1.3, coordinate transformations. So it says consider point P. Now the book has three R3, a point in R3. That is made a point in R2 to make it simpler and easier to draw. Consider a point P with coordinates x1, x2, x3 with respect to uh, a certain coordinate system. Let me actually swap which window this is in. Let's consider a different coordinate system, which is the prime coordinate system, one that can be generated from the original system by a simple rotation. That the coordinates of the point P with respect to the new coordinate system be x1, x2, x3, all with primes. And this is an illustration that they presented exactly. Mine down here is the same illustration with numbers, but this is the illustration from the book, what they call figure 1.2. The new coordinate system x1 prime, which in mine is just x, down here, is the sum of the projection of x1 onto the x1 prime axis, which they call OA. So this is the origin. And okay, so that's what I was mixing up last time. So this is the point we're looking at here. And this is the projection. So this is the place that we're projecting it to. So it's the x value itself projected onto the x prime. And then the y value itself projected onto the x prime. So let me think of the best way to draw this. So this is the projection onto the x, and that's the point that's projected. And this is the projection onto x prime from the y point. So we see that the projection is going in this direction. So it's just a matter of keeping in mind that the projection is directly from the y or the x aspect of the point directly to the axis. So it's not coming from the point and going down. It's coming from just the x-axis straight to the other axis. Just the y point straight to the other axis. So to draw the arrow in total, this is projected. Actually, let me do a different color. So this is projected here, and this is projected here. When I add those two together, that gives me the value on the X prime. And if we look at it, that makes sense. So basically we have the thing in blue plus this little bit, and that little bit seems to match this little bit here. So it seems consistent. And then it'll be the same thing with the Y prime. So the Y will project onto the Y prime coordinates here, and the X will project onto the X coordinate here. And notice that in this case, half of it is negative. So we have to subtract the lower part from the upper part. So last time I was extremely sleepy, so pretty sure that contributed to me not being able to see what it was. Was a busy time. And now we see that this triangle, now we see where the triangles match up at. So when I color coded this down here, when I color coded this, the green would be the X prime axis, the yellow would be the X axis, and the projection is in blue. So we can see how it is a lot clearer when we write it over. Right? Just clear enough. So going back to the algebra, considering the projection onto X prime of 6, 0, this is going to be X prime dot 6, 0 over the magnitude of X prime. This doesn't really help us because what's the magnitude of X prime? So the interesting thing is we don't have to have an actual number to make this work. In other words, I can pick anything along the X prime axis and it should work as long as I have theta. Problem is I don't have theta. So let's go to the book and see what they say about this. Now it gives us this equation, x1 prime equals x cosine theta, x1 cosine theta, x2 sine theta for y. Forgot I set this up so theta is 45. Well, in this case, we do have theta. So let's say if I pick some random numbers, let's say if I pick uh 20, 0. Well, maybe that's too difficult. Let's say 1, 0, the unit vector in that direction. So the magnitude of that would be 1, and this will still be 1, 0. So this would be 6 plus 0. So this would be 6, 0. That can't be right, can it? Check this message real fast. Right? Hate for it to be something that we have to just memorize. I mean, when I plug in the equation, like what I did right here, if I just remember the equation and I plug it in, it works. So the magnitude of 6 along the x will be, you know, like the value is just 6 cosine 45. And it gave us a good amount. Um, x2 was negative x1. So maybe we just have to remember this. We understand the transformation now. So at least we understand how the transformation goes. And I'm still not clear how to integrate this formula here from linear algebra, which, I mean, it should work. Maybe I need to just take more time and do it more slowly. Right, let's try it. So we have the equations there. And this, by the way, is negative x sine theta plus y cosine theta. So for now, that's something to write down in the formula sheet. Okay, so let's take a look at this. So we have the projection onto x prime of x, which equals the projection onto x prime of 6, 0, given that I had 6, 0 here. That's 6, 0 dot x prime over the magnitude of x prime times x prime. Now I picked one. It should work. Shouldn't matter what it is. Let's try a bit more in more detail. So that'd be 6, 0, dot product 1, 0 over square root of 1 squared plus 0 squared squared. I have to remind myself it's the magnitude the square root of the square root. Well, the magnitude squared is when you square it. And x prime we picked as 1, 0. So that will be 6 over 1, 6, 0 equals 6, 0. It was 6, 0. And the projection onto x prime of y, that's projection onto x prime of 13, 0. So that equals 13, 0 dot product x prime over magnitude of x prime x prime. So that equals 13, 0 dot 1, 0 over square root 1 squared plus 0 squared, 1, 0. So that's 13, 1, 0. So that equals 13, 0. Right, that doesn't seem to work. So maybe they mean something else other than projection. I mean, it seems like that's what they mean. Also notice that they say so just looking this over real fast, the image. I do recall Professor saying there was some typos in this book. Well, right, well, I won't spend too long on this. We'll just write down the formula. X prime equals x cosine theta plus y sine theta, and y prime equals negative x sine theta plus y cosine theta. So we have, and I can see the matrix here, cosine theta, sine theta, sine theta negative, cosine theta, xy equals x prime y prime. That's a transformation in 3. Now let's see what they have for the third. Let us introduce the following notation. We write the angle between the x1 axis and the x-axis as x1 prime x1. And in general, the angle between the x prime y-axis and the xj-axis is denoted by x1 prime xj. Furthermore, we define the set of numbers lambda ij is defined as cosine x prime I xj. So the angle between x prime and x is defined as prime x theta between y prime and y is defined as y prime y, and the angle between any two axes, let's say x prime and y, that's going to be x prime y. And lambda ij equals cosine x prime I x j, or lambda xy equals cosine x prime y. So I think all they're doing is just, in a complicated way, making this matrix here, lambda 1 1, lambda 1 2, lambda 2 1, lambda 2 2. Why did it have to be so complicated? Mm. So theta equals the angle between x prime and x. Let's say n prime and n. The equation of transformation now becomes so we have this equation here. So that equals x lambda 1 1 plus y lambda 1 2 row 1 column 2 equals negative x lambda 2 2 or 2 1 plus y lambda 2 2. Right? So all we did was just distribute the x and the y. The lambda 2 1 is, let me color code this. So all right, we have that. And I do recall in the one of my other classes, this being the a transformation. So I guess technically this was the 45-degree transformation. So I think I pretty much have it for 2 dimensions. I have to come back to the 3-dimensional version. The inverse transformation is x prime the quantity, so they're calling lambda ij is the direction cosine of the x prime I axis relative to the xj axis. Right, and we have the matrix already. It's making more sense in 2D rather than 3D. All right, here's a good place to stop. On the next page, on page 4, they start with an example. Maybe I'll come back on tomorrow sometime and we'll do that example and see what's going on. Well, thanks for joining. I'll see y'all next time.